Good morning. My name is Gregory Nyce, and thank you for giving me this opportunity to talk to you today about what I think will be a serious issue facing our society. I'll talk to you today about the challenges of feeding a world population in the future and a solution that will address those challenges. So for context, I'd like to go over the megatrends that are occurring in our century and how they will lead to food insecurity. First, it's estimated that by the year 2050, the world population will grow from 7 billion to 9.5 billion people. Climate change will lead to more extreme weather events such as drought and floods. Human impact on the environment such as pollution is not only harmful to humans, but also pollution is also harmful to plants. And finally, due to inappropriate use of antimicrobials, plant pathogens will continue to evolve to render once effective plant disease treatments ineffective. And this phenomenon is known as antimicrobial resistance. Left unchecked, plant disease will dramatically lower crop yields and thus the food supply. So as the population grows, the increase in food demand is estimated to be roughly 60%. But climate change, pollution, and antimicrobial resistance will all converge to apply constant downward pressure on our ability to produce food. Our technology directly addresses the rise of antimicrobial resistance and will result in higher crop yields while mitigating our impact on the environment. Our solution leverages the power of polymer science, and polymers are materials that are made from simple chemical building blocks that are chemically linked through a process called polymerization to make a new material. Polymer materials are everywhere, and it really would be hard to overstate the impact of polymers in our everyday life. I'd like to tell you about a new class of polymers that we've developed that will make treatment of plant disease easier, increase our food production while mitigating our impact on the environment. Now I'd like to tell you some important characteristics about these polymers. First, our polymers are potent and selective for killing pathogens. As I mentioned, they're less susceptible to the phenomenon of antimicrobial resistance, and they're environmentally friendly. So our polymers are effective against a wide variety of pathogens that cause bacterial, fungal, and viral infections. They're effective and potent at low concentration ranges, just requiring a few milligrams of polymer compound per liter to be effective. And our polymers are selective for killing bad pathogenic cells versus good cells. And in some cases, they're 10 times more selective than current products on the market. As I mentioned, our polymers are resilient to antimicrobial resistance. And so with traditional antimicrobial compounds, pathogens are able to adapt over time to make the antibiotic less effective and thus require higher and higher doses over time to control pathogen growth. As shown in this graph, only after 10 exposures to a common antibiotic, E. coli cells require 4 times the amount of antibiotic dose to control bacterial growth compared to the beginning of the study. In contrast, our polymer dose is constant over 10 generations, and we've even tested it after 30 generations, suggesting no development in antimicrobial resistance. Finally, our polymers are environmentally friendly, and here I hope to highlight what else can be done with an empty plastic bottle besides making other plastic bottles. So using our proprietary process, we first break down the bottle into its primary building blocks, and then we add other building blocks and polymerize that mixture to make our antimicrobial polymer in a simple two-step process. There are other environmental considerations that I would like to highlight. First, our polymers will decompose in the environment much, much faster than plastic bottles. It's estimated that a plastic bottle will take over 450 years or more to fully decompose in the environment, while our polymers will decompose in the environment in a matter of months or less. As I mentioned earlier, because our polymers are resilient to antimicrobial resistance, it'll be easier to control and treat plant diseases now and into the future. And also, less product will be introduced into the environment while still effectively managing plant disease. And finally, the results of a metagenomic study that we accomplished suggests that there's no changes in the soil microbiome after repeated applications with our polymer material. And thus, there's no indication that our polymers or polymer materials would be harmful to the environment. So how does it work? The polymer is engineered with basically 2 key features. The first is that the polymer is engineered with polymer positive charges along the polymer chain. These charges, positive charges, are attracted to the negative charges on the pathogen membrane surface. Then once the polymer is on the membrane surface, elements along the polymer chain can intercalate and disrupt the membrane, causing critical cellular materials to leak out and ultimately cause the pathogen's death. Now I'd like to talk about target markets and a case study that we've done with a company. So our initial target market is the agriculture antimicrobial market with an estimated market size of approximately $30 billion. And our total addressable market is the global antimicrobial market, estimated at $100 billion. There's lots of opportunities to apply our technology in different agricultural markets for many different types of diseases. I'm just going to focus on one disease known as citrus greening that resulted in a collaboration with a multinational beverage company. And this case study highlights our collaboration with the company, and how our polymer technology can solve real-world problems. The primary motivation for the collaboration was that the company's multi-billion-dollar orange juice business was under threat from the citrus greening disease. And the current solution, which I'll refer to as Compound X, works for them, but it had a lot of undesirable attributes, and the company was looking for alternative solutions. In addition, the company uses approximately 120 billion plastic bottles per year, and our polymer solution that repurposes plastic bottles to make antimicrobial polymers and requires low dosages amounts to treat plant diseases aligns with their internal sustainable packaging initiative as well as their sustainable agricultural initiative. So what is citrus greening? Citrus greening is just a disease that's caused by a bacteria that attacks the citrus tree's vascular system. It damages the fruit as shown in this picture, and it ultimately kills the tree. In Florida, there's been a significant decrease in citrus production over the past decade due to this disease. We did a head-to-head comparison of the company's current solution, Compound X, compared to our polymers, and there are a few key takeaways. First, our polymers vastly outperform Compound X. Our compounds were 100 times to 1,000 times better at killing the citrus greening bacteria. So now I'd like to cover these other topics, and first I'll talk about value creation. So everybody's familiar with the notion of recycling, where the value of the new bottle is equal to the value of the used bottle. But in contrast, our approach is to upcycle the plastic bottle, resulting in a 10 to 100 times step change in value from a used plastic bottle to our polymer products. There's a lot of large corporations in the agrochemical space. We differentiate ourselves from their offerings by how our polymers are sourced. We make them from plastic. Our polymers are resilient to antimicrobial resistance, making it easier to treat plant diseases where theirs are not. There's no concern of getting cross-resistance between plant and human pathogens, and we don't use heavy metals in our formulations. We have a robust patent portfolio, and it continues to grow. We have a great team with over 50 years of combined experience in chemical, polymer, and chemical process development. We're pursuing a licensing business model, which will generate revenue from licensing fees and royalties for our proprietary polymer compounds. We'll generate revenue from licensing fees using our proprietary process to make these compounds, and also generate revenue from our engineering service. And so our ask today is an initial investment of $2.5 million for a 25% stake. This money will be used to grow our polymer pipeline, as well as complete milestones related to scale up and start the registration process with the EPA. Food security is one of the major challenges of this century, and our technology will make plant disease easier to treat and manage, resulting in greater efficiencies, greater crop yields, and doing it in an environmentally friendly way. Investing in this technology will result in significant value creation, but also will have a strong social impact. Thank you for your attention, and I look forward to answering your questions.